So, so today we'll be speaking about and be covering about this brain boundary engineering. So till now, what we have covered is from the starting classes, it's and the starting sessions. It's about what is a grain boundary, okay, regarding what kind of a defect is a grain boundary, then what are the types of grain boundaries, and the simplest classification of the two types of grain boundaries primarily, that is the low angle grain boundaries and the high angle grain boundaries, using the Reed-Shockley model, where of course 15 degrees is taken as the benchmark for separating the low angle boundaries from the high angle boundaries. And of course, the reason behind that also we have covered in one of the classes, I mean one of the earlier sessions. Then we have also discussed about how a typical grain boundary energy versus misorientation plot looks like, where in a cubic material where there is a 4-3-fold axis of rotation, and as a result of that, we have some symmetry in the grain boundary energy versus misorientation plot. And of course, we have certain in the high angle regime, there is more than 15 degrees of misorientation. We do also have certain local minima, which we also describe as the points of special high angle grain boundaries, or the low energy high angle grain boundaries in the cubic materials. So, of course, for your level, to explain that, I mean the simplest grain boundaries in those, those grain boundaries may also be termed as the CSL boundaries, or the coincident side lattice boundaries. So, so today, now let us discuss why have we learned all these things. Of course, so there has to be some significance, some engineering significance of all these concepts, which have to be merged into one, and definitely all these converge into one thing, that is the grain boundary engineering. So first of all, let us learn what does this terminology, that is the grain boundary engineering, actually mean. It's nothing but it's the practice of obtaining microstructures with a high fraction of boundaries with desirable properties. Now, when I use this term, a high fraction of boundaries with desirable properties in a microstructure. So what do I mean by this boundaries with desirable properties? It's in general, these properties are associated with boundaries which have simple low energy structures. Okay? Simple low energy structures in a sense that we talk of in case of high angle boundaries, because generally a microstructure will have much higher fraction of high angle boundaries than low angle boundaries typically. So in a high angle regime, the points of local minima. Okay, so those boundaries are basically having low energy, and why they are having low energy, as that we have discussed in one of the earlier sessions. It's because of the coincidence of the lattice points after regular intervals. Okay, so for example, if we talk of sigma 3, okay, boundary, it's every third lattice plane between the two adjacent lattices or adjoining lattices will be in continuation with each other. Okay, so like this. So and such low energy structures are in turn associated with the CSL boundaries that I have already said while I was talking about the sigma 3 boundaries. Then fourth, this grain boundary engineering is at present largely confined to FCC metallic systems such as stainless steel, nickel-based alloys, lead, copper, etc. Of course, and why they are mainly limited to the FCC metallic systems is because the because the FCC metallic systems show a high possibility. I mean, the atomic arrangement along the 111 plane or the octahedral plane in the FCC metallic materials, which is the ABC stacking typically, which would be the ideal stacking there. There is a high chance of formation of stacking bonds and high chance of resultant twinning there. Okay, so along those planes. So as a result, as a result, so this is one of the reasons. And then the second reason is that not in all FCC metallic systems, for example, if we look at the case of austenitic stainless steel, is fully austenitic stainless steel, 3XX series. Okay, so it's if we are now talking about the stainless steel, we are talking about the AISI 3XX stainless steel, which is having a low stacking point energy. Even nickel, which is having a low stacking point energy. Copper has a low stacking point energy. So there is a high chance of the of the twinning, to accommodate plastic deformation. There is mechanical as well as, and also there's a high chance of formation of the annealing twins, which form during the growth accidents. Okay, so grain growth accidents. So of course, so these are the factors. Okay, so these are the factors in the FCC metallic systems, which where we definitely see that the twins. There's a huge chance of twinning, and definitely as a result, we have green boundary engineering largely is concentrated at present in those metallic materials. Of course, if you look at the case of aluminum again has got an FCC structure. Again, it has got one plate and atomic and the ideal where the ideal atomic stacking sequence should be ABC, 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 and so on. But definitely in the case of aluminum, the problem is that the stacking point energy is very high, and in those cases, the you know the um, so the chances of twinning during plastic deformation is much lesser as compared to those metallic FCC metallic materials which have got low stacking point energy. Now, similarly, this is again the logic which can be used to say that why in the case of BCC metallic systems, so the BCC metallic materials, green boundary engineering, uh, green boundary engineering is very hard to employ. I mean, of course, we cannot say that in any BCC material. For example, if you look at alpha iron, we have we have a number of CSL boundaries, right? I mean, which has got a BCC structure, we've got a number of CSL boundaries. Of course, that has been reported in a number of literatures. But now the problem with alpha iron or any typical BCC material is that it's the atomic stacking sequence, the atomic arrangement along the most close plate 110, or even any other plate, low index plate. So generally the atomic arrangement does not allow under normal conditions. It does not allow, or under equilibrium conditions, it does not allow the formation of twins. Sorry. So the formation of twins. So as a result, it's very hard to obtain a twin microstructure in the BCC metallic systems. The BCC metallic materials. So grain boundary engineering is very hard to employ there in the BCC metallic materials. Okay. So so generally, what does the GB consist of? Very simple. So GB consists simply of repeated cycles of deformation and annealing, chosen so as to generate large fractions of special boundaries. Of course, the low energy boundaries or the low energy high angle boundaries, of course, and to avoid development of the strong recrystallization tensions. So this is one of the aspects. I mean, we can avoid development of strong recrystallization tensions, which can be which can generally degrade your mechanical properties. But it also, not only mechanical properties, but these special boundaries can also guide in a lot of things, because these special boundaries, first of all, have low energy associated with them, and the drain boundary energy associated with them, as compared to random angle boundary. And as a result, these boundaries can, in principle, reduce the reactivity of the material to the external, chemical agents, for example, etchants and so on. For example, when you look at the case of pure metal or any metallic material which is getting etched. So, what is etching? Etching is nothing but preferential corrosion, and of especially the grain boundaries, which are the high energy regions or the high energy sites in microstructure. Okay, so in an equilibrium microstructure, I must say. So there, it seems that and why those boundaries are getting preferentially corroded is because of their high grain boundary energy, and especially if they are the random high angle boundaries, they will have a higher tendency of getting etched or undergoing preferential corrosion as compared to that of a low energy boundary. Okay, so definitely. So in that case, so then there's a reason, why we are able to see the etched microstructure. But again, there's again, if you look at the problem of over etching, because again, if a microstructure is having too many high angle boundaries, I mean, especially after recrystallized condition, when it has too many high angle boundaries, too much of high angle boundaries rather. So there, the boundary energy, the overall boundary energy in a given section of the microstructure is very high, and as a result, when we etch it, it's there's a huge chance of over etching, which we definitely do not want, because in that case we'll end up having corrosion products deposited at grain boundaries. Although we are able to look at the grains, but we don't want such boundaries to be decorated with corrosion debris or the corrosion products. So definitely, when we have a grain boundary engineered microstructure which is having special boundaries, a large fraction of special boundaries, and a reduced volume fraction of the high angle boundaries, which cannot be, unfortunately, be completely eliminated. It's very hard to do that. I mean, it's nearly impossible to do that rather. So there, the chances of preferential corrosion is much lesser. Okay, in special boundaries or the coincidence lattice boundaries, as you can say, associate with the cubic materials. FCC materials primarily. Okay, so and so what we can definitely say is that the grain boundary energy is mostly linked to sigma less than or equal to 29 boundaries, but definitely I would rather put it as this way, that is GBE in most FCC metallic systems is mainly linked with sigma 3, sigma 5, sigma 7, sigma 9, and okay, and hardly sigma 11 boundaries. And although people have reported this thing sigma 29 boundaries, but then you see sigma 29 boundaries means that every 29th lattice plane will be in coincidence with each other between the two adjoining lattices. Okay, so there, I mean, in such cases, such boundaries first of all are very less in terms of volume fraction in a given microstructure. Number one. Secondly, as compared to the sigma 3 and all the low sigma value boundaries, sigma 5, sigma 7, sigma 9 boundaries. But then, secondly, if so, even if such boundaries are there, it is very unlikely that such boundaries are going to make much change in much. Or a significant change in the properties, okay, of a given material. So okay, although people have reported this, but among these, what we should say is that among these sigma 3 or the twin boundaries are mostly the lowest low energy boundaries, and can be should be the lowest low energy boundaries as compared to sigma 5, sigma 7, and sigma 9, and must be exploited to achieve grain boundary engineering microstructure. And this is exactly the reason why GBE at present is largely confined to FCC metallic systems, which have got low stacking point energies like austenitic stainless steel, nickel alloys, even nickel, even copper, lead, etc. So, okay, now let us look at a very simple demonstration of grain boundary engineering. Now, if you look at microstructure, which has got a certain hexagonal grains and which has got R, L, sigma, and where R is nothing but the random high angle grain boundary, L is a low angle grain boundary, sigma is the CSL boundary. So there, what we can say is that, when we are deforming the material in a tensile fashion by sigma, applying a certain amount of stress sigma, then what we can say, let us consider two sides, okay, side A and side B. Now let's say that there is a crack which is propagating along the random angle boundary from side A, and once it reaches a triple junction between L, R, and sigma, where L is having the least energy, grain boundary energy, sigma is having a comparatively high grain boundary energy as compared, comparatively high grain boundary energy as compared to L, but a much lower grain boundary energy as compared to R. So of course that depends on the value of sigma also. So there, so there, what the crack tends to do is that the crack first reaches a triple junction, then it tends to propagate along the sigma boundary in an intergranular fashion, and then after a certain point of time, it changes its mode of propagation to a transgranular mode, and then propagates through that second grain, and then again changes its propagation mode to intergranular, and again reaches another triple junction between L, R, and sigma. But now it doesn't propagate through the sigma boundary at all. Rather, what it tends to do is that is again. So that's the reason I said it also depends upon the value of sigma, whether the crack will propagate through it or not. Of course, whether what is the, because that sigma value decides its energy. Okay. So okay. So now what the crack tends to do is that instead of propagating in an intergranular fashion, it tends to propagate in a transgranular fashion. Number one. Second thing, if you're looking at the point B, we again see that there's a crack propagating along R, random high angle boundary, reaching a triple junction with R and sigma. But sigma is having a much lower energy as compared to two R's. And now the crack tends to propagate along the R, and then again it tends to propagate along another R, because this is the other triple junction between RR and sigma, and then it reaches another triple junction of RR and sigma, again tends to propagate through R. Again, now it reaches a triple junction comprising of three R's, three random angle boundary, tends to propagate through that, and then reaches another triple junction between R and another sigma. Now it tends to propagate through another R, or the another random angle boundary, because definitely sigma has got a much lower energy as compared to random angle boundary. So here, basically what we now tend to see is that if in a microstructure we can reduce these R's, okay, these random angle boundary, and reduce and replace them preferably with sigma or L. Definitely, it's very hard to replace these R's with L, because L is generally a subgrade boundary. It's generally we do not see such an arrangement, where this kind of a boundary may be termed as L. What we instead would see in an actual microstructure is that we would see an R and we would see a sigma here, and so the sigma has to the volume fraction of sigma has to go higher up, okay, as compared, and the volume fraction of this R in the given section of a microstructure has to come further down. And of course course, in that case, we will see that the microstructure gets more resistant to crack propagation. As we can definitely have seen in the first case, that is when once the crack the A crack reached LR at sigma triple junction, it tended to propagate through sigma for some time, okay, and then again in an intergranular fashion, and then changed its mode of propagation to transgranular fashion. Okay, so but in the second case, where we see that only that there is RR and sigma, the crack tended to propagate for the case of B crack. So the crack tended to propagate only through the R boundaries, random high angle boundaries. So these things must always be kept in mind. That so this is a very simple way of even illustrating how do we need to, and why, of course, do we need to attain grain boundary engineered microstructure, achieve grain boundary engineered microstructures. First of all, for the case of metallic materials mainly subjected to structural applications, we need to have crack resistance, a huge crack resistance for the material. So that's the first reason. Okay, so that's something which comes definitely to your mind when you see this particular schematic. Any kind of crack. It can be a tensile crack, it can be fatigue crack, and so on. So now if you look at so this is a very good illustration from one of the earlier publications in this field. It is by Sumatra Mandal. It's by so it shows this one interesting thing, that if you look at this microstructure where the black colored line is a random angle boundary and the red colored line is nothing but a sigma 3 boundary. It's a twin boundary. So there what we can have is that so when we give the thermomechanical processing or certain things okay, that I will again discuss in the next slide, in order to attain grain boundary engineered microstructure, what we end up essentially having is that we end up reducing the volume fraction of the high angle boundary, random angle boundary. As you can see, the extent of black lines in this case has been reduced as compared to this case. And of course, the other thing that has been added is the sigma 3 boundary have increased in the volume fraction, and also sigma 9 boundary has also been induced. Okay. Now, as you can again see further, so it's been taken from Randall. This is an excellent book on grain boundaries. So there, what we can again see is that if we are having more, more extent of employing more extent of thermomechanical processing, TMP, what we end up then essentially inducing is we end up inducing more amounts of random angle boundary. Here we are inducing sigma 27. We can also end up inducing sigma 3 or even sigma 9 or any sigma. It again depends on the material properties completely and also on the thermomechanical processing parameters that we employ. Okay. Now, so the simplest way to describe what is grain boundary engineering is that if you look at a bunch of hexagonal polycrystals which are comprising of random angle boundary and which are again comprising of twins, maybe these are mainly annealing twins because they extend throughout the entire grain. I mean, as I've already discussed in one of the earlier sessions. So it's a sigma 3 twin boundary. So then once we employ certain TMP, which is not fixed of course, because which keeps on varying with the different materials. It depends a lot on the material system. So then what we ultimately end up having would be something like this, where we have the volume fraction of high angle boundaries, that's the random achieving, much lesser here, 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 and we also end up having a much higher fraction of the sigma 3 boundary, and we also keep on, we have also induced sigma 9 boundary, and we have also induced sigma 27 boundary. Of course, this kind of an arrangement will have a much lower grain boundary energy because of all these sigma boundaries. Which are replacing the random angle boundaries as compared to the first case. So the first situation where we had only this random angle boundaries, which are with a large volume fraction, and within the grains we had only this sigma boundaries, or the sigma twin boundaries, simple twin boundaries. Okay. So with this now let us briefly discuss about the methodology to achieve the grain boundary engineering your engineered microstructures. So it's the TMP is the most effective and the most widely used. What is TMP? Is the thermomechanical process. However, there is no fixed TMP schedule that can be applied to achieve GB microstructures in all materials. This could, however, be attributed to large number of variables associated with the TMP process, such as material properties. Of course, the first thing that matters is there is particularly the stacking fault energy. That is because of that I already described. If we are looking at FCC materials which are having the low stacking fault energy, and we are looking at FCC materials with high stacking fault energy like aluminum. mean, the green boundary energy, the green boundary engineering is very hard to employ in such high staying point energy efficiency materials. Number one. Secondly, it's also the same reason where we will have very very high staying points energy in the case of BCC materials. The green boundary energy, engineering is very very hard to employ there. Okay. Secondly, it also depends on the initial microstructure, because whether it is an equilibrium state or a non-equilibrium state, or it has got, or first of all, mainly depends on what is the initial fraction of high angle boundaries in the initial microstructure. Okay, and okay, so based on that, we need to decide. Okay, so we need to decide the TMP schedule, of course. Now let us discuss about this TMP. Just briefly mention about the TMP parameters. There is a plastic deformation mode that we apply as thermomechanical processing, whether it is compression or tension or rolling. What is the extent of plastic deformation which is employed? Whether even in whether it is in compression or tension or rolling or mixed mode, whatever. And lastly, the annealing time and temperature. Of course, it's a thermomechanical processing, so thermal parameter has to be there. So it's annealing time and temperature, which is again going to influence a lot of things. So, so this is okay. So this is all about the methodology to achieve the green boundary engineering. Of course, there are other methods also. I'm not entering into them because mainly this is the most widely used method, TMP. Okay. So, so now this is the last slide of today's session, and this is also the last session of the term of this semester, where I'll be just briefly touching upon the green boundary sliding and how the green boundary character influences the green boundary sliding in metallic materials. For example, this has been taken from aluminum. Okay, and this has been taken from this particular lecture note. So there, what we can see is that if you're looking at random high angle boundaries, they may easily slide and undergo preferential fracture. Okay, so if you're looking at all the R's, random high angle boundaries, there is a huge chance that if you look at this crack, which is propagating all the way throughout the random high angle boundaries, and okay, and there's a huge chance that these cracks will continuously propagate throughout the entire thing, throughout the entire random angle boundaries, and these will ultimately lead to preferential fracture. Okay. So secondly, the random boundaries are fast paths for atomic diffusion, whereas low energy boundaries are not. And why? Because because they're random angle boundaries, because the atomic arrangement in such boundaries is much random as compared to the low energy boundaries, which have got a certain extent of ordering, okay, or rather to say crystallographic ordering, which is associated with them. Okay, so as a result, there is a certain amount of closeness, or they are a bit close packed as compared to the random ion boundaries. So that's the simplest explanation that we can give you. Okay, for atomic diffusion. Okay, so last one is that so this leads to structure difference. So definitely, so such kind of differences, if you look at sigma 21, sigma 7, so here you don't see there is a crack formation, but a crack propagation. Rather, even if you see here, so there's a crack propagation along this R, and it keeps on extending towards R. Once it reaches a triple junction, although it is not propagated, but it does not, although the crack is not propagated along this R, but now the crack neither propagates along the sigma 21 as well. So sigma 13, sigma 7, sigma 21, all these boundaries generally are much resistant to crack propagation as compared to the R boundaries. Even the L boundaries are the most, rather the L boundaries in that case are the most resistant to the crack propagation. Okay, so so definitely, so such a situation where you have R's, okay, where you have random angle boundaries, so this leads to structure dependent diffusion, controlled integral of gravitation, and fracture during plastic deformation at high temperatures. So so with that, I conclude today's session, and if you have any questions, please feel free to ask. Please feel free to also post in the Google Classroom. Thank you for your patience, and I'm open to questions now.